Okay, welcome back to another video. So in this one, we just finish up or we review that example we started in the last video and give you the numerical values and show you how to do it a little more. So just as a reminder for completely confined aquifers, we saw when we did that straight line method that there's basically never, it never stops dropping. So the drawdown keeps going up and up and up and up as time goes on. So you never really reach an equilibrium. At some point you're going to run that well dry, if you will. That's another way to say it. For the leaky confined aquifer, like we saw last time, what we would expect is then to have some limit at some point, at some time, where your drawdown is constant, right? It stops dropping because now we have a recharge boundary. We have water coming from somewhere, essentially. Okay, and we also saw that now we have a two-argument Wells function, right? The Artesian Wells function has two arguments. So the u, like before, which is the equivalent of time, and then now we have that r over b second argument that gives us that family of functions that we've seen last time. So again, if we take a look at this Artesian Wells function in a semi-log plot, right, to again reminiscent of that straight line method that we did for the confined aquifer, you can see that the Thies curve here at the top again is that straight line method, but for the semi-confined or the leaky confined aquifers, now we have these flat curves, if you will, that show that the drawdown is actually constant after some time. And of course, the more leakage you have, the faster you get to that equilibrium, if you will, between the recharge and the drawdown. So if there's a lot of water rushing into your well, soon after you start pumping, everything is going to be in equilibrium. If there's only a little bit of leakage, well, you're pretty much almost confined, so you're up there. Okay, so again, just a way to think about those curves. Okay, so let's look at an example. So you are given a discharge of 1,037 cubic meters per day, and you are given drawdown data in an observation well that is located 128 meters away from the pumping well. Okay. Now here's the data. So again, this would be drawdown versus time, and here's your Wells function. So this is 1 over u versus WU. Okay, and the first thing to do is match your curve, right? So again, the questions are, what is the transmissivity and the storativity? That's always what we want to know. If the aquitard, so this is information you actually need if you want to calculate the hydraulic conductivity in the aquitard, because of that Darcy flux that we use for the leakage. You actually need to know the thickness of that thing in order to back calculate its properties. So oftentimes it's not that important to know the hydraulic conductivity of that thing, but anyways, that's something to keep in mind, and we'll see this in a couple more examples. We also have a MATLAB script for this. Obviously this is from MATLAB plot here, so you can fetch that online and then use it or anything. We also have an Excel format, an Excel version, and I'll talk about this and I'll do a whole video about this later. Okay, so let's start to fit. There it is. So if we fit, so this is the same as the last video, right? So if we fit the data, we see that we're along this orange curve. So we go from the bottom. So this is the orange curve right here. So R over B equals 0.3. And now we have a match point here. So we're saying that 1 over U is 1, so U is 1, and WU is 0.1, 0.2, 0.25, maybe almost 0.3. And here is time, which is again 0.1234, 0.4 minutes. Is that minutes? I don't know. We'll see. And drawdown here is roughly 0.1 something, 0.1, I don't know, 0.15 or something. Okay, so now we have all the information we could, right? So this is again R over B equals 0.3. So now we read all the numbers from the plot and we can plug them in our equations. So here it is. So using this equation, right, we can measure the transmissivity. So again, put transmissivity here and S here. So we read S, so we know what it is. So the transmissivity is the discharge we know, right, the pumping rate. 4 pi, the drawdown, we just read it from the plot. And then the WURB, we also read it from the plot. So they're basically here and here, right? So plug everything in and find the transmissivity is 146 square meters per day. Here, using this equation for U, right, the argument, we can calculate the storativity. So again, storativity is the unknown. Now we just calculated the transmissivity, the time we read from the plot, U we read from the plot, and the distance to the observation well is given. So we have everything known but the storativity at this point. So you calculate transmissivity first, then the storativity, and that gives you again 1.25 E minus 5, accounting for minutes to days conversions, right? So you have to convert. Okay, so again, this looks like a normal storativity for a confined aquifer. Again, E minus 5 is pretty standard. Now, since B prime is given, right, in this particular problem, you can actually calculate square root of, okay, sorry, B prime here equals this. So we use that to calculate our K prime, and now we can find that K prime, meaning the hydraulic conductivity of the aquitard, of that leaking layer, is 0.011 meters per day. And again, notice that how this is pretty low, right? This is a hydraulic conductivity that is, impeding the flow. That's why it's a semi-confined aquifer, because it's still, that top layer is still pretty impervious. It doesn't let a ton of water through, yet it does let some water through, and that's why, we have all that complication. Now, a quick note here, there's an Excel file that, again, I'll do a whole video about how to use it, following this one probably. But, this is all semi-automated, I guess, in that Excel file, meaning that all those equations, I just entered into the Excel file. So if you put all the knowns in those red cells here, you can see that this is the same problem as we just did manually. So it's 1,037 cubic meters per day. We have an observation well 128 meters away, right? So all those red, all the red cells, you'll have to input basically what you know. So when you fit the data, you see that R over B is 0.3. Now you plug that 0.3 in. If you know that B prime, if B prime is given to you, again, red cell, then you could put that in. And if you know all those things, then you can, the Excel sheet will essentially calculate automatically, all the remaining parameters, right? So it'll give you S here, you can see is 1.24 E minus 5, just like we did before. So again, I'll do a short video on how to use it, but this is essentially, the same as we just did, just in Excel and automated. Okay, thank you, and I'll see you in the next video.